little bit on cloud computing. Everybody's heard this word, cloud computing, and you know, some people know what it is, some people have no idea what it is. And just to tell you, basically, the way you view it is a sort of a shared configurable computing resource on demand, provisioned by a service provider of some sort. There's service providers out there. And they provide a network or something like this inside this mysterious cloud. And it's not like what we used to do with client server. You knew exactly which computer you were talking to. Here you talk to the cloud, and the cloud answers you. But you have no idea what's going on inside. You're in a big fog, basically. So basically, like I said, it's the new way of talking to things in the internet. It's basically a collection of integrated network hardware, internet for connection. The keyword here is what's bold here. It hides the complexity of what you're doing. So basically, the cloud server basically tells you, or doesn't, you don't worry about the details. You just worry about your application, and it worries about where it's logging backups, storage, whether it's sitting in Newark, New Jersey, or whether it's sitting in Paris, France. You don't care. And that is all taken care of by the provider. And it provides services and things like this. And so he said, like, it's remotely hosted. It's ubiquitous service and data available from everywhere. So basically, as the internet, basically, you don't care where the cloud is, but you can access it basically from everywhere. And of course, this is the bad news. It's commercialized because basically you can't get something for nothing, because basically they have to make money too. And so, yeah. Who uses the cloud, for example? Basically, you're using it every single day. If you use any of these services here, you're basically talking to the cloud. And a lot of these things are based, I mean, Gmail based obviously on Google platform. I forget exactly, YouTube or something. They all chose their particular servers. There's this type of different cloud flavors, we'll say. Software, you have software service, so basically it provides software. Infrastructure provides more than just software. It provides you all sorts of stuff. Platform to put, for example, your resources, or a desktop. And for example, we have one type, Amazon Web Services. That's sort of infrastructure. They provide an infrastructure. Google Platform, Google Apps. They platform as service. Or we have other ones. But anyway, they provide infrastructure where you can perform all these tasks, and they combine, mix and match. And so basically, sort of the architecture is, you're sitting up here with this stuff in the middle, and the infrastructure is service, and they take care of it for you. Now in this talk, I'm going to talk about my experience with the Google Cloud Platform, the implementation of my particular thing, ChemConnect. One question you can ask, why did I choose this one? I don't know, I'm a Google fan, what can I say? I have Gmail, everything. And, but also it's connected with a lot of Google philosophies that I seem to be using, and it had actually the right sort of infrastructure that I needed. There are other ones, for example, Amazon is also one. Even, for example, I think, yeah, depending on what you want to do. Services provided, for example, here we have a whole range. This copy paste from the Google service. Computing environment. So basically, instead of having your own computer, you can actually hire their computer, and basically they take care of everything. So basically, instead of having your, I don't see a computer here anymore. In any case, instead of having your standalone computer somewhere in your desk or underneath your desk serving your particular thing, you can provide that. And then there's storage. There's all sorts of different types of storage. There is one type of cloud storage, which is basically if you want to store files or whatever, images and things like this, like if you have all your YouTube videos or something like that. Now I'm using something, well, yeah, this one, and particular I'm using is App Engine, which is basically an app type of thing you can use in your phone or whatever, through your browser, basically. Then we have, like I said, cloud services, which is using. Now, the last three, Cloud Data Store, SQL, and Bigtable, are basically databases. SQL, I think whoever has done any sort of programming knows what SQL is. Sort of a very standard database that's been around for a long time. Data store in Bigtable. Bigtable is actually what Google actually uses itself to do all of its storage of database. So the fact that Google knows everything that in your life is actually stored in Bigtable. I'm using data store, which is sort of in between these type of things. The app engine basically is, like I said, it provides, if you program in Python, Java, or any other language that you happen to prefer. This is talking to the programmers here. I don't know how many I'm talking to. But in any case, provides the language that you can actually, so if you write in these languages, then you can use the app engine to upload your service. They provide extra stuff. So an API is an application programming interface. What this means is basically a library of stuff that you want to do that you don't have, somebody's already programmed it for you. And for example, my data store, my database access, I have one that does all the work for me in terms of getting things from the database and getting things back again. So all I have to do is do a call and say, get me something from the database, and it takes care of the details. And these are all sorts of details, but you can see it has a range of applications, YouTube stuff, if you want a YouTube in your application for some reason or another, all the Google stuff, and whatever. And of course, what you have, if you put your application on the Google platform, then of course you have monitoring services, how much space you're using, how much your networking is using, and why this is important for you, because basically, I'll get into that later, basically it means that's what it's costing you. They have minimums that doesn't cost anything, but if you start doing a lot of traffic, a lot of storage or something like this, then it's going to start costing you. And then, for example, the database stuff, I have tables of database information that I'm using, and you can access this directly, so you can access directly through some sort of monitoring device, which my raw data that I'm storing in my raw database. And just to give you an idea of sort of the development cycle for doing something like this, you have basically you can have, oh yeah, well actually the whole arrangement is a client-server arrangement. You have the server side, which for example my software is living on the server. It generates an interface that you see on the client side. So that's actually when you're using it, this is actually what you see. And then when you press a button or you do an action or something, it sends it to the service and it interacts with your app engine, which is doing sort of the work, and the cloud data store, the database, interacting with this thing. So this is sort of the setup of the whole business. And to develop this, of course, you need it's helpful to have some sort of programming environment. This is a classic one, Eclipse, which is available online, are basically sort of a standard free programming environment. But actually, on top of that, they provide services. So basically, with a click, I can deploy. Deploy means put it onto the server so it's usable for everybody else. And yeah, so they give you a way to actually program easily. So basically, you program. For example, I'm programming in Java, and I do all my classes and do all my things in Java, and then I say, okay, deploy, put it onto the server, and it does it. So the development cycle basically looks like this. Offline, in my local environment, I program, try it out locally. The app engine and the cloud store is sort of simulated locally, and I can do sort of a development cycle there and try it out. And when I'm satisfied that it's working locally, then I deploy it to the cloud. And then I'm actually using the app engine and the Google Cloud stuff on their server, on the Google platform. And then that's actually when you want to use it, when you publish it to, like for example, the demonstration, you'll be able to talk directly to the Google Cloud. So talk to my application that's sitting on the cloud. So I'll give you an IP address, and you'll see this business. And like I said, you can't get something for nothing. And some of these prices don't look very expensive. You know, gigabytes, for example, storage, gigabytes per month is 18 cents. But when you're talking about the amount of storage that, for example, I'm going to be using terabytes of data, you start multiplying that by 1,000 or 10,000 or 1,000,000, then it starts to be significant. And this is when I need help. But in any case, or that's why it's, this is why people charge for these type of things. But anyway, and then also the networking, if you have a lot of traffic going back and forth, you can talk about here, you do have minimums that if you don't have very much traffic going in and out of your application or something like that, they give it to you for free. But as soon as you exceed this, then they start getting worried, and then they start, so you have to be aware of these type of things. Okay, so now I'm going to change, so that's sort of what it's built on, sort of the infrastructure. Now I'm going to talk about the application itself. And like I said, there'll be a demonstration of this. You can actually use it yourself during the demo session. What I want to do is to make the immense amount of data available to the combustion community, but not only available, but searchable. And this is fine. Well, let's see, do I say this? Yeah. And once again, this is not necessarily restricted to accepted published data, although at the moment is going to be. What I'm doing is parsing readily available from Galway, for example. I'm stealing all your data, by the way. And from Lawrence Livermore and Princeton and San Diego and things like this that have published their, with a click, publish their data, and making it available, but also I call fine-grained. So what I'm doing, actually, like for example, what I've done at the moment, I've taken a ChemChem mechanism, broken it down into the species and the reactions and the NASA polynomials and things like this, and have each one of those bits of information as individual entities within the database. So basically, if you want to know a particular species within a mechanism, you do that. Y'all get into that later. And I want to, very important in this whole business is to recognize the interdependencies between the data. So actually, so the whole database is based on relationships, and this is what I'll get into more directly. And this database is set up so it can be actually used as the database itself can be used as an analytic tool. The motivation, of course, you've seen this one before and before. This is basically, we're going from paper publications. Now we have an immense amount of data. We want to make this data available, make it searchable, so we need this virtual environment. The key concept in what I'm presenting here is metadata. And keywords, basically associating keywords with the data type, data source, for example, the origin of the data, the time and place it was generated, and the time and place actually was entered in the database, all sorts of information, who also is involved. Data qualifications, for example, with each data point you also have some sort of, this is actually work in progress, but some sort of qualification in terms of sharing. At the moment, who owns the data, or who owns the data, and also, which means who inputted the data in a certain sense. But also how public you want the data. Do you want it just available to yourself? Do you want it available to your friends or your social group? Or do you want to have it perfect, or to the whole public? And then quality is something also work in progress that can be defined in many different ways, and either by a keyword or, but that's something we'll be working on. I think I'd rather do some sort of passive. So basically, it's based on data relationships to other objects, and it's basically something called ontologies. What is this ontology? Basically, the purpose of it is to find relationships between data. Not my idea. It came from the semantic web. Basically, this is what the web does to interconnect all the data on the web, what Google or all these search engines do, how you find things. And of course, the motivation is to search a large body of information and finding relationships between them. The basic entity in this whole business is called a research description language, which essentially means you have a subject, which in my case is basically a string, a keyword, a text. You have a predicate describing this, what does this mean, and connecting to the object. So the subject is subject of the description, the predicate describes it, relationship between the subject and the object. Then the object itself is what you're pointing to in a certain sense. So to take the example of a ChemChem mechanism, you have the object. For example, the first one is sort of name of a mechanism that was been inputted, has reaction, and then it has this reaction here. Or this molecule has standard enthalpy, this one. Or this reaction is a submechanism, so. Or, for example, this reaction has a product, has a thing. So basically what I'm doing is I'm taking the ChemChem mechanism, breaking it down into many of these relationships. And the key word here is basically you're connecting unrelated data. One thing is, my keyword here is passive. Because what I'm doing is I'm making connections, like within a particular ChemChem mechanism, I'm making all these connections. If I have another one, I'll explain this a little bit later, the same species, for example, this one all of a sudden gets related to this one. And so actually, even though you had no idea about this other one, you actually now have a connection between the two. So basically what you're making is a whole network of connections between the data. And so now independent data sources become interconnected. And so basically if they share the RDF subject or they share the RDF object, they are now connected. And once again, the key word here is passive. Just a quick note, because everybody talks about standards. The role of standards in this whole thing is actually, in one sense, is how the data gets in there in the first place, because I have to, for example, what I'm doing is parsing files, so ChemChem is a standard, some XML files will be a standard, things like this. So I have to parse it to parse out this individual information. But once I parse out this information, I can't say have no use for standards, but actually it's not an integral part of the database itself. But of course, as new standards come up, you can supplement the data, make new relationships. For example, if your data all of a sudden gets assigned a DOI or your publication, then you can say this piece of data has this DOI, but then behind this piece of data is all your stuff. So all of a sudden this DOI gets associated with everything passively. So you didn't have to physically associate the DOI with everything else. Through traversing the network, you come up to its relationship. So what you have is basically a large network of interconnections. Each bond, since we're chemists, we can talk about bonds. Each bond between each of the nodes is an RDF. And so basically what I'm doing is restructuring the data. So instead of blocks of data, basically what I've done, So instead of blocks, basically instead of blocks, I have interrelationships between the blocks because of this RDF. So now it's not blocks anymore. It's basically a bunch of interrelated concepts, interrelated. So basically you have one piece of data, another piece of data, and if they, like I said, if they share something in the middle, then they get connected to each other. To give a semantic web, how this is done on the web, for example, we have a description of a book with the author URL. And the semantic web in this case adds meaning to the independent sources. So basically what they've done here is you have connections, and these are sort of the connection between the publisher and the author and things like this. But the interesting thing here is, for example, you have two different independent sources they know nothing about. One's an English version of the book, one's a French version of the book, but they happen to have, for example, one URL that's actually in common, and this is the way the semantic web has been using this type of thing. They have this. Now all of a sudden, since these are common, you can merge the two. And now what ends up happening is now you have a connection. So with this one, without even knowing about it, you've connected the French, Frederic can read the French version of it, and everybody else can read the English version. Sorry, Frederic, I didn't. Is she here? Ah, she's not even here. Good. So, once again, the fine-grained information. So I'm blasting apart a mechanism into fine-grained information. I put this in red. That's hard to read, but in any case, this is actually what I've done now, basically blasting apart a ChemChem mechanism. This is actually what's implemented at the moment. And this will be demonstrated today. Other sources, of course, One of the main ones, one of the main goals I'll do later in a minute is actually automatic generation stuff, because not only do they have mechanism information, but they also have an extra bit of information, for example, 2D structures and things like this. So now passively, once again, if you have a mechanism, Henry, you made one, you have a certain molecule. If it's been, if I can somehow through the network bind it with an automatically generated one, then I can through the network say, I know the structure of that particular label that you happen to give that particular molecule. And this is an example of that. For example, we have two mechanisms here. This mechanism has this species. This species is an isomer of this particular one. This one as this species is an isomer. So now we have a connection between those two particular species. And now we have a connection between those two mechanisms. And then, of course, you have other sources between, for example, even a computational chemistry thing. You can go through, it has thermodynamics, and it goes through. And so basically what you're doing is you're connecting up. If there's a connection from here to here, then you have a connection between the data of each one of these things. So basically you're linking models together. This is a little bit of picture from the interface, which is, not the best at the moment actually, but so basically the query method here, the principle is you give a keyword, it searches the objects or the subjects of the RDF and comes back with these relationships. And basically the search process at the moment is basically traversing, as a tree at the moment, traversing the network of possibilities. So here we have, I have one UC San Diego natural gas mechanism is a mechanism. So I have this, say, what mechanisms do I have? And then on top of that, it says that, well, within this mechanism, for example, is the that particular reaction. Now I have this longer name because that's actually specific. That reaction, particular one, is specific to this one. And then that itself is being broken down to which species it has, and I'll get into that later. Oh, here it is here. So then that one has a reactant, for example, NCH3, but that's at the moment in particular to that particular data piece in that particular mechanism, because that also has pointers to the NASA polynomial information, the transport data, and things like this. And then we can, once again, we can connect to other mechanisms. For example, you have a species name, or you type in an isomer, C3H7, and then it says, well, which ones have this isomer? And then it comes up with, well, this the UC San Diego actually has two versions of this, the N and the ISO version. But the GRI, for example, has just the one version. But then you can say, okay, now you've connected, in one sense, you've connected all three of these methods, all three of these, and you can start using this information, finding out, which one do I really mean. And in fact, I'll give you an example of trying to decide how we can actually say conclusively that the one in GRI is talking about the same one that's being talked about in this UC San Diego. Because one important fact and one reason why we have this problem is because in the mechanism, that name is just a label. It has, in one sense, you could call it George for all you care. The fact that it has C3H7 is just the fact that you want to give, you don't want to say George goes to Ralph plus Harry. You want to say that CH3H7 decomposes into something, so you can interpret it with your eyes. And so basically, like I said, you have this relationships. Now, and then in the background is this RDF. One thing just to note here, I don't say you have basic creation date, but you also have access point, so you can say it's public. I haven't done that into I often have access. I haven't developed that completely, but there is an opportunity. So with each data point, you have this one. So now, one reason why I'm using data store is the fact that this is getting beyond normal database stuff. It's called a thing called NoSQL databases. One of the keywords here, it's scalable. In other words, as your database grows, it knows how to scale it and how to manage this, and this is what the service does for you also. And one particular reason why I'm using this particular one, this says highly scalable, meaning, okay, it's for not, I don't know, this is a relative term which is called large jobs. But this also has, this can sort of simulate the way you use it. It's sort of like this SQL stuff. There are other options. For example, like I said, the Cloud Big Table, which is actually what Google uses in storing all their particular information. And that's this, you notice the difference in adjectives, massively scalable as opposed to highly scalable. So I think mine is highly scalable instead of massively. I don't think I'll get to the Google stuff. And once again, using a database as an analytical device, you can say, how does a certain species react? For example, you can just give it keyword of a species or an isomer or something like that. It finds it as a reactant, as a product, gets a set of reactions. And not only from the one particular mechanism you're talking about, it's actually from all of them. So you can actually start searching, for particular, if you want information about a particular species, you can start looking for it. For example, here. So I typed in, yeah. So here, looking for C3H7, it says is a product, is a reactant of these guys. It's also a reactant, a product, or the I version. Then we have also the GRE version of the whole thing. So basically, this is the type of stuff you're getting out of the database. These are copy-pasted screenshots of the mechanism. And the last one is the GRI. You can also have, in one sense, a path of your search path within the interface. You see in the black here how I got there from my searches. And reaction information, we have other things, the coefficients associated with it and things like this. And this is actually, there's one button that says give me the reaction information in different forms. This will be developed later. Something also developed is basically save to cart in a certain sense. If you're looking for information, you want to keep it separate, and so you put it there. And then there's reaction pathways, for example. Species is the product, is a reaction. So basically, you can follow this chain. So for example, if you want to say a pathway within a mechanism or something like this, you can just keep going. And now all of a sudden, you have a connection between two species. OK, that's 3 reactions down from my particular one. So that's automatic within the whole thing. And so basically, in the background, you can start doing these type of things. And if you want to expand the database, you can actually make a new thing. Species has a path. Species 1 has a path to species 2. You can actually supplement your data. And once again, since each data point is sort of independent, this is sort of a passive way to expand your data set. Same principle of species between mechanisms. Basically, you come up with sets of reactions for this one, sets of reactions with this one, and compare the two. It's a little bit more complicated. You have to compare them as species as isomers. But in any case, you can say, OK, this one is similar to this one because they match in a certain set for reactivity. Because so the structure of a species in ChemChem is actually, in ChemChem is basically given by how it reacts. And so it's sort of implicitly or passively given as it reacts. And this is the way you start connecting this stuff. And I'm going to skip through because I'm getting a bit late. One step further, of course, like I said, is if you connect a normal ChemChem one with an automatic generated one. The automatic generated one has also, in addition, its 2D information. So now you can start associating 2D information with your information. Data inputs, for example, this is sort of the way it looks. You give a description of the data, and then you can upload it directly from a URL, or you give it as text or a file, for example. The look and feel, just to tell you, one of the reasons I'm using also Google Web things. One interesting thing about this one is that if you look at it on a laptop as opposed to a telephone, it automatically rescales your the look and feel of the whole thing. In the background, there's query. You have an account sign in, basically because you want to decide what data you have access to and what data is to be shared. And actually, for me, it's a little bit more a little bit security also that we don't that I can kick people out if they don't have the right access. Also, there's a thing called transactions. One of the interesting things about transactions is going to be that since there is a lot of data and you'll get a massive number of hits, you want to start filtering these type of things. And so basically you want personal filters and general filters. For example, if Google uses this type of technology, for example, if each one of you types exactly the same search in their Google engine, there will be massively different search results, actually, because Google knows everything about you. And so it says, he doesn't want to know about that, he wants to know about that. And they do this from collecting this type of information. Also, e-commerce uses this. If you go to a book site, it says, I would suggest you read these books, and it's also based on this type of information. Future directions, I'll go into this more in the code because I'm running out of time. And basically, to be continued, and if the gods of the internet and the demo effect doesn't affect things, you can try it out yourself. Thank you.